So thank you guys for joining today's webinar, Benefits of Using Iron Coagulants in Wastewater Treatment. I'd like to give a special thank you to our sponsor, Kemira. Kemira is a global chemicals company serving customers in water-intensive industries. They provide expertise, application know-how, and chemicals that improve our customers' water, energy, and raw material efficiency. Today's presenters are Brett Offerman, who's a Senior Account Manager for Kemira. Brett has been working for 45 years on drinking and wastewater industry, and 25 of those years with Kemira in managing major water and wastewater accounts. I'd also like to introduce Richard Waterous, who's a Senior Account Manager as well. Richard has 34 years of industry experience, and 17 of those years are with Kemira. He has extensive experience with potable water and a wide range of wastewater treatment applications. Both presenters plan to keep you very engaged today. And with that being said, I'll now hand it over to our presenters.
Thanks, Dylan. Brett and I are here today to provide you with an overview of the benefits of using iron coagulants for various applications in wastewater treatment. The first application that we will cover is odor and corrosion control. Hydrogen sulfide is a colorless gas with a distinctive smell of rotten eggs. It is highly toxic and has a very strong smell even at low concentrations. H2S can be detected by the human sense of smell in very low concentrations. Because hydrogen sulfide is heavier than air, there is a risk that the concentration in sewers will reach dangerous levels. There have been numerous cases of workers being killed by hydrogen sulfide gas while working in sewers. H2S is 18% heavier than air, and the gas-air mixtures can be explosive. In concentrations as low as 10 parts per billion, it can cause nausea, headache, and conjunctivitis of the eyes. H2S is extremely toxic at levels above 500 parts per million and causes instant collapse and likely death at levels above 1,000 parts per million. When H2S reaches elevated levels, concrete corrosion rates can be approximately 1/2 inch per year. Many municipalities have encountered catastrophic collection system line failures due to the presence of elevated levels of H2S. In fact, collection system collapses due to H2S origin corrosion are the driver for many municipalities to initially implement a collection system H2S control program. In the last couple of decades, there has been a trend of increasing H2S levels in sewer systems. Effective industrial pretreatment programs that have reduced heavy metal sewer discharges and the transportation of sewage over longer distances are likely contributing factors. Bacteria has a unique ability to convert H2S to sulfuric acid in the presence of oxygen. Sulfuric acid accumulates on the surface above the flow line. One such bacteria is Thiobacillus, Latin for eats concrete. The gas released in the pipe from slow-flowing or stagnated wastewater reacts with moisture on the walls to form sulfuric acid, which corrodes concrete and ferrous metals. Benefits of iron used for sulfides control include the following. Iron salt addition binds sulfides virtually immediately and remains bound for the duration of the treatment process. The resulting bond is very robust and can be accomplished many miles upstream of a plant's headworks. Iron salts addition eliminates sulfides even to non-detectable levels if desired. It prevents corrosion and noxious odor. Iron salt use is cost effective. And very, very important, iron salt use yields quantifiable downstream benefits unmatched by competing approaches. Iron reacts with sulfide species resulting in direct precipitation complexing of dissolved sulfides as water-insoluble iron sulfide complexes. Irreversible binding of iron with dissolved sulfides leads to elimination of free sulfide for the duration of the wastewater treatment process. The robust iron sulfide complex formed with our treatment program keeps sulfides bound throughout the entire treatment process, including anaerobic digesters, preventing the release of harmful H2S gas downstream. Many of our customers add iron many miles upstream of the treatment plant to maintain low levels of dissolved sulfides throughout the collection system. This is unlike other chemistries which provide a more localized solution. Ferric and ferrous chloride and ferric and ferrous sulfate can be utilized for effective H2S control. The robust iron sulfide complex formed with iron addition keeps sulfides bound throughout the entire treatment process, including anaerobic digesters, preventing the release of harmful H2S gas downstream, unlike competing chemistries. Both bottles in the photo are samples of raw municipal wastewater plant influent containing high levels of dissolved sulfides drawn from a customer's headworks. The bottle that is black has had iron sulfates chemistry added to bind the sulfides present. The black micropin flock that you observe is iron sulfide, the result of the iron chemistry pulling the sulfides out of solution and complexing with it, with the resulting insolubles precipitating out in the plant's treatment process. H2S, gone untreated, can and is detected at numerous locations throughout a wastewater treatment plant's process, including the headworks and bar screen zone, aeration basins, anaerobic digesters, and dewatering process, even in the dewatered biosolids. If liquid phase dissolved sulfides are present, H2S gas can be generated and released at a location in the process where agitation and aeration is present. Air scrubbers can only handle a limited H2S load. Treating the sulfides in the solution form prevents harmful H2S gas forming downstream, resulting in fewer odors and less corrosion. Let's now move over to Brad, who will talk a little bit about CEPT.
Thanks, Richard. Good info. Now let's talk about enhancing settling in the primary clarifiers with either ferric chloride or ferric sulfate coagulants. Even though there might be iron still available at the headworks from the upstream treatment Richard discussed, there won't be enough to enhance settling. Chemically enhanced primary treatment, or CEPT, has been around a long time and used quite successfully around the country and especially in California. CEPT is a solution for wastewater treatment plants dealing with increased process flows, higher than normal TSS and BOD, and treatment bottlenecks or plant expansion restrictions. CEPT involves the addition of ferric chloride or ferric sulfate, with or without polymers, at the plant headworks or primaries, and implementation of CEPT programs results in increased removal of organic and particulate matter in the plant's primary clarifiers. Proper application point and mixing is essential for CEPT, and the polymer addition point is crucial as well, as there must be sufficient mixing time for the ferric iron coagulant before polymer addition. Benefits include reduction of TSS, BOD, and phosphorus loads to the secondary aeration systems, increases plant throughput rates, reduces energy by lowering the aeration cost, reduces dewatering cost, and increases biogas production. Iron coagulants create a large flock, and with the addition of an anionic polymer, the flocks are bound together and settle well. Other properties of iron coagulants include the following. They're very effective in heavy metal removal. They create a dense, fast-settling flock. They work over a wide pH range. They control the formation of H2S gas in the headworks and downstream processes such as primary clarifiers. And all iron coagulants have low freezing points, but it is recommended to heat trace pipes and valves in cold weather applications. There are a variety of process issues that CEPT can address, such as fluctuations in influent water quality caused by higher TSS and BOD due to water conservation, and the need for more capacity in the primary clarifiers. Some agencies are designing aeration systems around CEPT with lower TSS and BOD with reduced tank sizes and air needs. By using CEPT and increasing primary sludge, the biogas production will increase as primary sludge has more volatile solids than secondary sludge. Typical plant solids are 50-50 primary secondary sludge, and CEPT can tip the balance to 60-40, primary, secondary, or higher. The chart on the right shows the various energy cost factors, with aeration representing up to 60% of the cost. Iron coagulants bind sulfides in the primary sludge, and when it is pumped to the digesters, it reduces the H2S level in the digester gas, and due to the high volatile content of the primary sludge, results in more methane production for cogeneration facilities. And it also eliminates corrosion concerns. So in review, the benefits of CEPT include increasing primary clarifier removal rates, reducing aeration process energy use, lowering FM ratios and increasing aeration process capacity, improves the biological process as the iron is a nutrient and some plants are nutrient deficient. It also increases primary sludge with higher volatile solids to increase biogas production and reduce CO2 footprint. Now let's talk about some case studies. This is a partial list of plants using ferric chloride and ionic polymer for CEPT and their increased removal efficiencies and downstream benefits. Orange County Sanitation District in Orange County, California has 2 plants, both formerly primary treatment only, and they designed their new secondary aeration systems based on the use of CEPT and obtaining 40 milligrams per liter TSS in the primary clarifier effluent. City of San Diego Point Loma is a primary treatment plant utilizing CEPT to reduce the solids in the ocean discharge and has been using CEPT for over 30 years. City of San Jose, California has been using CEPT and has many downstream benefits as well. And in Miami-Dade, Florida, there was a trial performed in 2016 and 17 with very successful results. I'll pass it on to Richard.
Thanks, Brett. Ferric chloride or ferric sulfate are commonly used to enhance sludge dewatering and yield a number of benefits. These include the following. Iron use eliminates struvite depositions and prevents future struvite scaling. The photos on the right show typical weekly struvite deposits on the centrate line and centrifuge bowl for a large municipal plant in the southeast. The after shots were taken after 4 months of iron use. Iron use improves dewatered cake solids, typically from 3 to 7 percentage points. Iron use for enhanced dewatering reduces dewatering polymer demand as much as 55%. Better centrate quality. Iron use can significantly improve solids capture rates, resulting in higher centrate filtrate quality. Reduced TSS and phosphorus via centrate or filtrate return to the treatment process contributes to improved treatment plant performance and reduced costs related to chemical usage if CEPT is utilized, and improved aeration operation. Increased dewatering capacity. Increased machine throughput rates can exceed 35%. Enhanced liquid solid separation increases water release rates that enables higher sludge loads to dewatering. Increased machine throughput rates can reduce the number of machines in use, reduce machine run times, and potentially manpower hours. Lower costs for transportation and sludge disposal. Higher dry solids in dewatered sludge equals fewer truckloads of sludge hauled. For cases where the biosolids are incinerated, higher cake solids equals increased energy recovery. There are platforms now available to the marketplace that can automate and optimize iron addition for this application. Four reasons why the use of iron for enhanced dewatering may be a good solution for your plant's operation. Struvite elimination results in reduced process downtime, maintenance, and equipment replacement costs. Drier cake solids, reduced energy consumption and carbon footprint for drying and transportation of sludge, improve machine throughput rates. Reduced phosphate load returning to the plant process. Finally, higher quality centrate, filtrate water returned to the plant. Reduced phosphorus and solids load, improved treatment. The use of iron addition to enhance solids dewatering yields a number of sustainable benefits. These include the following. Reduction in CO2 generation, tied to reduced machine runtime, reduced truckloads, improved plant performance tied to improved centrate quality, and so on. Increased dewatering capacity, energy savings, freight savings associated with reduced truckloads hauled for disposal, saving in sludge disposal costs. And finally, technology now exists to provide customers with 24/7 program transparency and KPI monitoring. The majority of enhanced dewatering applications begin with the plant's need to mitigate struvite formation in deposits. As benefits to the dewatering process associated with ferric iron addition became apparent, smart process control systems were developed which optimize chemistry feed in the dewatering process while controlling struvite formation. Struvite control. So what is struvite? Struvite is a nuisance crystal that often forms in anaerobic digesters, sludge transfer lines, dewatering equipment, and centrate lines. Struvite forms when magnesium, ammonium, and phosphate ions are present under specific conditions. Struvite deposits can seriously limit machine performance and restrict sludge flows. Regular shutdowns to process operations may be necessary to pig, jet, or physically replace piping or other equipment due to struvite depositions. The addition of iron-based coagulants remove phosphate ions from the digested sludge and subsequently eliminates struvite formation. An additional benefit of phosphate precipitation is a reduction in the phosphate load returning to the plant process from centrate and filtrate lines. Enhanced dewatering. The application of a ferric iron coagulant also conditions the sludge, boosting the liquid-solid separation and thus enhancing the dewaterability in the solids handling process. This results in higher cake solids, reduced dewatering polymer use, reduced hauling costs, increased machine throughput rates, and higher solids capture rates, resulting in reduced energy consumption and smaller carbon footprint. Now back to you, Brett.
Very good. Thanks, Richard. You mentioned phosphorus binding to prevent struvite. Now let's talk about removing phosphorus with ferric iron coagulants in the wastewater stream. As many of you know, state regulatory agencies are mandating lower phosphorus limits in NPDES permits into receiving waters. Agencies will typically design biological processes to nitrify and denitrify ammonia nitrogen and can include biological phosphorus removal as well, also known as BioP. We will discuss the use of iron coagulants to enhance this process and or to reduce phosphorus in plants without BioP. Benefits of iron coagulants include improved water quality and compliance. Ferric iron coagulant addition works to settle out not only the metal phosphate compounds just formed, but also any other suspended solids in the waste stream, as previously discussed. It enables reliable compliance with stringent phosphorus limits in NPDES permits, sometimes as low as 0.5 milligrams per liter phosphorus or lower. Downstream benefits and cost savings. As previously discussed, some additional benefits of using ferric salts are that they remove hydrogen sulfide, enhance cake dryness, and treat struvite in the entire process. Optimized coagulant usage results in less chemical sludge and therefore lower biosolids disposal costs and reduced polymer usage costs. Ferric iron salts can be added in the primary, secondary, and tertiary areas of a wastewater treatment plant, depending on the need of the agencies and the treatment process. Primary addition removes phosphorus at the front of the plant to alleviate overloaded secondary systems and binds the phosphorus in the primary sludge. Proper addition points and mixing is essential to ensure proper removals. Ferric iron addition into the secondary system has the advantage of proper mixing and therefore better settling in the secondary clarifiers. Tertiary addition is more of a polishing process after BioP to achieve the lower limits, but might be an issue. It is the last line of defense. Determining the coagulant dosage level begins by establishing the soluble phosphate level in the wastewater to be removed. Phosphorus in wastewater is separated into three main fractions: inorganic orthophosphate, inorganic polyphosphate, and organically bound phosphorus. Chemical phosphorus removal is based on two different mechanisms. Chemical precipitation of phosphorus includes converting the dissolved inorganic phosphorus compounds, mainly phosphates, to a low solubility metal phosphate through the use of iron-based metal salts. At the same time, metal hydroxide forms and creates a gelatinous flock that aids in binding together the metal phosphates and the suspended solids, which includes organically bound particulate phosphate in the wastewater. The contaminants that are present become enmeshed in the hydroxides, causing almost all remaining contaminants to be swept down with the settling hydroxide. This process is known as sweep coagulation. When dosing iron in the presence of soluble phosphorus or phosphates indicates an insufficient coagulant dosage. The presence of insoluble phosphorus or organically bound particulate phosphorus points to poor settling conditions, which are normally addressed through the adjustments of hydraulic loading rates, mixing adjustments, polymer dosage adjustments, or in the worst case, providing additional flow capacity. Phosphorus can be removed with 90% efficiency, and the final phosphorus concentration may be lower than 0.5 milligrams per liter. The chemical dosage for phosphorus removal is the same as the dosage needed for TSS and BOD removal, which uses the main part of these chemicals. Some plants can add just ferric iron coagulants at the various locations mentioned to achieve the desired removal efficiencies, and those with BioP may be facing lower limits unattainable without the addition of ferric iron coagulants. Now let's discuss a case study in North Las Vegas, Nevada. The water reclamation facility runs an average daily flow of 17 million gallons per day with a 25 million gallon per day max capacity and utilizes submerged membrane bioreactor technology to produce reclaimable water. The issue: discharge permit requirements only allow 35 pounds phosphorus per day, or approximately 0.23 parts per million during March through October. The plant needed a solution for reducing phosphorus levels during these months. The solutions: studies conducted at the North Las Vegas facility showed an increase in phosphorus levels when water temperatures exceeded 82 degrees Fahrenheit. Ferric chloride was introduced to chemically remove phosphorus compounds by adding 200 to 400 gallons per day from March through October. The result: improved water quality, phosphorus discharge limit compliance, improved biosolids production, and biosolids process cost savings.
Thanks, Brett. Recapping, the addition of iron for a number of different applications within the wastewater treatment process can yield numerous benefits, including the following. Iron eliminates sulfides to non-detectable levels and prevents corrosion and noxious odors. Debottlenecking key aspects of the treatment process. Increasing plant throughput rates and process capacities. Increasing the production and quality of biogas. Reducing treatment costs. Optimizing treatment and plant performance on a 24/7 basis. Phosphorus discharge limit compliance. Generating quantifiable downstream benefits that treatment alternatives cannot offer. Sustainability, reuse of raw materials. Reducing the wastewater treatment plant's carbon footprint. And finally, there's an emerging market for digitally enhanced process optimization platforms that ensure optimal performance associated with iron use on a 24/7 basis.
Very good. Richard, you mentioned sustainability. Sustainability is of growing interest, and a large part of the raw materials are from recycled sources such as high quality ferrous iron and other materials. Many public agencies are starting to add sustainability requirements for their vendors, and they also have their own sustainability goals as well. As you see on the infographic, these are United Nations Sustainable Development Goals, which guide the decision of both public agencies and vendors. Okay, Richard, take it away.
We thank the audience for participating and now welcome any questions that you may have. I see that there are a number of questions posed.
Let's see. Okay, I see one guy says, any hazards of adding iron? Well, as with any chemical, you have to have a safe handling, and always refer to the SDS for proper handling of any chemical, proper PPE, it is essential. I don't know if that really answered the question.
Brett, further to your answer, obviously, iron salts are classed as hazardous. So it's essential to have double lines. And Chimera generally utilizes a completely self-contained storage and feed systems that eliminate the spill factor. But as Brett noted, you need to take necessary precautions.
Mm-hmm.
The next question from Megan, how long is ideal to wait before adding polymer after the addition of iron? Iron works quite effectively. It's essential to have rapid mixing and dispersion upon introduction to your process. I would say that typically, and again, it depends on the application, but it could be as short as really 30 seconds following iron addition, where you consider the addition of iron of polymer. And the next question, what is the reaction time for iron coagulants? Again, depending on the application, and I'd say almost universally, the reaction time is quite rapid. In other words, for sulfides control, when I say quite rapid, I would say within 30 seconds, as is the case for all of our applications. Brett, would you concur?
Absolutely.
Do you want to take the pH question, Brett?
Yeah, basically, most wastewater is neutral pH, and the additional ferric iron will lower the pH slightly, but as with any coagulant, there is that sweet spot of pH range. So you're pretty much good with the neutral pH. If you have a high pH wastewater, you obviously want to bring it down with an acid, HCl or sulfuric acid, just so you're not wasting the coagulant to drive the pH down.
Next question are, what are the potential byproducts in the effluent? When adding iron to your process, a reaction takes place forming an insoluble iron hydroxide complex. That's the byproduct that is found in the residuals. And I can tell you, the experience for both Brett and I is being that actually having iron present in biosolids is attractive from a commercial standpoint, from an agricultural application standpoint. But our expectation is that there is no real negative impact on the biosolids, that it's a favorable impact. Right? Can you comment further?
No, I just hope Thomas answered your question. There is really no byproducts. If you're referring to the wet testing on the sludge, I think Richard answered that.
Next question here from Nate. Where does the H2S go? Once again, Chimera's approach is to be proactive and to prevent the form of the release of H2S by capturing the dissolved sulfides in the liquid phase. Once the iron complexes the dissolved sulfides and forms an insoluble iron sulfide complex, it's not released downstream. Brett and I both have numerous customers where they utilize an iron salt and collection system in the collection system for H2S control. In some cases, the iron is added 25, 30, even 40 miles upstream of the plant to achieve a target headworks dissolved sulfide rate. With the iron, it effectively binds it and keeps it bound, and it's very robust. I have examples here in South Florida of plants where our target is to maintain we add iron in the collection system to maintain a target headworks dissolved sulfide level and corresponding H2S level. We're able to achieve that. And at one plant in particular that I'm referring to, the digester H2S levels, despite having no iron added anywhere beyond the collection system, the digester H2S levels remain below 25 parts per billion. So very robust. Very robust.
Yeah. So the second part of Nate's question is it trapped in the solid phase? Yes, it is. It as Richard says, it forms an iron sulfide, thus preventing it from breaking out as a gas.
Brett, do you want to take the next question from Alex?
Yeah,
and then
Alex,
accept?
great question. I was just at the CWA conference last week, and Molinaire company did a presentation on the use of nanobubbles. It's quite interesting. I learned about those last year, and there's a couple of plants here in Santa Barbara County that are using it. And they mentioned that it works very well with the iron coagulants. It's quite an interesting process. If anybody has any, should look into it. It was quite interesting, but it does assist in that, if that answered the question to Alex.
The next question, Brett, from Andrew Shaw, regarding the opinions on different forms of iron, ferric versus ferrous, chloride, sulfide, and other solutions. Obviously, depending on the application, you require the ferric only Fe+3 in the form of ferric sulfide or ferric chloride. For example, with CEPT, you require the coagulant, which is the Fe+3. For sludge conditioning, you require Fe+3. Conversely, depending on the application point, for effective H2S control and for phosphorus removal, both ferrous, which is Fe+2, and ferric, Fe+3, or a combination of the two can be proven effective.
Yeah,
it's very much a site-specific situation. As part of Chimera's service, we visit plants to conduct detailed site surveys. We gain a better understanding of the customer's pain points and needs, and from that we can recommend the optimal chemistry. We can recommend the optimal injection point. Brett, do you want to take the next question from Martino?
Yeah, explain a bit more in depth why there is an increase in biogas production. Not clear to me why iron coagulants lead to higher volatile solids. And I think one of the other presenters, Andrew, kind of answered that. And I mentioned you increase the primary sludge production, much better TSS capture, more sludge to the digester, is more biogas. And as we mentioned earlier as well, the primary sludge has more volatile solids versus the secondary sludge. So that's why you have more methane production.
Brett, if I could expand upon that briefly. Here in South Florida, we obviously have a major issue with H2S, with elevated H2S levels. One of Chimera's long-term customers, Miami-Dade, historically had major issues with sky-high digester gas H2S levels at their two plants, South District and Central District, that process biosolids. At one plant, the H2S levels in the digester historically exceeded 10,000 parts per million. At the other plant, they historically exceeded 6,000 parts per million. With Chimera introducing an effective iron approach to reduce the H2S levels at both of those plants, we were able to see, and there was a paper published that I can provide anybody who's interested in it with the details. But by adding iron to both of those applications, targeting digester H2S reduction, we were able to bring the levels down to the 400 part per million range, which is as per the plant guideline. And in doing so, methane production, or methane levels for both plants went up approximately 10 percentage points.
Okay, Richard Brooks asking if we have resources or services that guide proper mixing design.
Absolutely, Brooke. I'm a member of our advanced water treatment team. My colleagues and I, one of the things we do, we travel all around the country. We visit wastewater plants all around the country that have various process challenges where Chimera can offer solutions. Part of what we do is conduct a very detailed plant site survey. We conduct very detailed laboratory tests to identify a problem and provide a solution. So the answer to that is 100% yes.
Okay, Brad's asking about discussion on potential of iron felling on UV sleeves. Great question. As you know, a lot of plants are switching to UV for disinfection, and you really have to have the optimized dosing. The iron typically will end up in the sludge, as we discussed, and and not carry through the system. But certainly if you have an overdose situation or you're too far downstream, then you could have a potential iron fouling of the sleeves. But there again, that's where the proper dosage and the proper iron coagulant is of importance.
Question from Mr. Salenza or Miss Salenza, I'm not sure, male or female, speaking about the use of ferrous versus ferric coagulants. Once again, ferrous is Fe+2 is not a true coagulant. Ferric as Fe+3 is really the true coagulant. So ferrous applications, while effective, are limited. They're again, assuming that the injection point is correct, ferrous can be very effective for H2S control. Ferrous can also be very effective for phosphorus removal. However, if you were looking at a pure chemically enhanced primary treatment application or a enhanced dewatering, enhanced sludge conditioning application, you absolutely require the iron to be in the ferric form.
Huh. And Randy says, what are the other coagulants? Are these results derived from inorganic or organic coagulants? So I'm not really sure which part of the presentation you're referring to. If you want to put in the chat and specify, but basically we're talking about the inorganic ferric coagulants. And then I did mention the anionic polymer, which is an organic coagulant. So when used in combination, you get really the more bang for your buck, at least in the CEPT application.
Brett, do you want to take the next question?
Sure. Jonathan says, if iron chloride is added, does the plant need to dechlorinate? Absolutely. As we're discussing, the iron chlorides is mostly up front in the plant or in the digester. It has nothing to do with the dechlorination system at the end of the plant. I shouldn't say absolutely. Obviously, if you have to dechlorinate, you continue to it. It'll have no effect on the disinfection process.
Question from Renee Duguay regarding price increases. Yeah. Renee, I could comment that we feel confident that iron pricing has stabilized, and in some cases we expect it to be reduced. But I will tell you that's even more important, that some of our ChemConnect platforms are utilized to optimize chemistry usage. But we remain confident that despite the increases, that iron remains to be a very competitive option for finding a treatment solution. The next question from Christian about the potential change in polymer charge. The answer is yes. There are times where, again, because iron carries with it a positive charge, there are times where we have seen that the dewatering polymer that proves to be optimal could carry with it a slightly lower cationic charge, which contributes to additional savings. But again, that's a site-specific thing, and as part of our normal routine, when we're looking at enhanced dewatering applications involving iron, we will screen a number of different polymers, including the incumbent, to confirm if the incumbent remains the best option or if there are more effective options. Question from Kevin. Absolutely. The products that we have discussed today are available in Ontario. Chimera, for example, has a very large production facility in Montreal. We additionally have a large terminal in my hometown, which is Brantford in Southern Ontario, as well as in Toronto. So without question, absolutely yes.
Martino asks, is Chimera providing any type of solutions for on-site chemicals generation? At this time, no, there's no on-site generation of the ferric or ferrous chlorides. We do have a new ChemConnect X performic acid disinfection technology that's on site that we can talk about some other time.
Question from Randy. Would a structured polymer provide better sludge dewatering with proper sludge conditioning? Randy, I would have to say that's very much a site-specific answer, depending on the type of dewatering equipment used and the characteristics of the feed sludge. But I can tell everybody present almost universally when iron is used, and there are very detailed PowerPoints showing the mechanisms behind the liquid solids separation when utilizing iron. But without question, as noted, the use of iron as a sludge conditioning agent enhances that liquid solid separation process, reduces dewatering polymer usage, and improves cake solids. But again, Randy, your question, I would have to say, is quite site specific.
Yep. Renee's asking about coagulants dealing with calcite buildup instead of struvite buildup. I don't know where Renee's located. I think he's in Ontario, but I don't know. I'm not familiar with calcite. Richard, are you?
I am not.
Well, maybe Renee can clarify that in the chat, and we can get a little more information. And here is Isaias from San Jose. Yes, exactly. Isaias been a long time proponent of iron up there in San Jose. And
Next question, where is the best location for introduction for the iron coagulants? Once again, that's somewhat site specific. It depends on the application, and it depends on the goals of the iron addition. But once again, that's as a service that Chimera provides our customers and our prospects. You know, once again, we can visit your plant. We can conduct a very detailed site survey. We can uncover what your goals associated with using iron are, whether that's enhanced phosphorus removal, whether that's chemically enhanced primary treatment, whether that's enhanced sludge dewatering. And observing your plant, we can identify the optimal injection point as well as the optimal means of injecting the chemistry.
Okay, Ryan's got a comment about a member jurisdiction with a very high sulfide discharge. For years, the industry and that jurisdiction utilized bioxide, but recently switched to ferrous chloride. The addition is within the collection point at the furthest point, and we are now trying to get a handle on the change to our processes. Nothing negative, but we were finding that while our final effluent is really clear, less than 5 milligrams per liter TSS, we can filter less sample. Any input or experience on this? We can filter less sample. I don't understand what that means. Ryan, maybe you can elaborate in the chat.
I can tell you this much, Ryan. If you have made the switch to ferrous, it may be helpful for Chimera to come and do a site survey and run some tests. We also, as an aside, we have a platform known as OCC that actually, you know, again, because the audience knows, for collection system H2S control, the dissolved sulfide load can vary dramatically due to a number of factors. We have a platform that actually measures the dissolved sulfides, and depending on the levels and depending on the treated objectives, our platform can automate the dosage.
Okay, Richard, it looks like Jeff responded to Ryan's question about the TSS. He says it looks like, I just lost it. He says it sounds like the TSS is down, but maybe total dissolved solids are up, leading to filtering challenges.
Admittedly, I can't comment on that. We don't see that problem for our H2S control clients, and neither do you, Brett.
No. Looks like we're getting short on time here, Richard. What else you got here? Oh boy, there's so many here.
Reuse water, absolutely. If your plant seeks to enhance the quality of reuse water, much like a CEPT application, or also bear in mind, these products, ferric chloride and ferric sulfate, are heavily in use for potable water treatment. So regarding the question, can these products be used for reuse water treatment? Absolutely. And the next question, the typical dosage rate for H2S control in a municipal wastewater treatment plant. Generally, we see for every pound of dissolved sulfides, the demand is between 1.3 and 1.5 pounds of iron as Fe.
Yep. And Isaiah did refer to the 2021 WEFTEC publication on CEPT for a lot of these questions. Appreciate that. Somebody asked about the concentration of ferric. It's 38 to 42%. If you're looking at 30%, you're probably talking about ferrous chloride. That came from Randy. Somebody asked a question about coagulant mixing times prior to polymer addition. I think we kind of covered that. It's very rapid mixing. Polymer could be 30 seconds to 5 minutes downstream. And a lot of it really depends on the wastewater quality.
The question regarding which is better, ferrous or ferric for H2S removal at a municipal wastewater treatment plant. The guideline would be, my guideline would be, if you're looking at collection system H2S control, if available and cost effective, my first inclination would be to go with ferrous.
Yep. Somebody asked about it. It's a precipitate form of phosphorus, bioavailable. Can it be used by crops when the biosolids land applied? Absolutely. And as you know, even just iron alone is a great nutrient for crops, as Richard mentioned.
And if anybody on that note, Brett, if anybody's interested, we have published papers that we can provide anybody in the audience to verify the bioavailability of the phosphorus bound with the iron.
Yep.
It's slow release, so it's very effective for crop.
Yep.
For crop treatment.
And Sahul asked if we had any case studies on removing copper. Yes, I'm sure there's some. Just reach out to us. We can list that to you. Paola asked about negative effects. They determined that ferric chloride destroys equipment. I think that really depends on the application point and the proper mixing. You know, the small amount of ferric you're adding compared to your wastewater stream is pretty small. Richard, you want to expand on that?
Well, yes, obviously you need appropriate materials of construction. So Chimera, for any of you that are interested in looking at iron as part of our service, we would obviously, as Brett noted, we would recommend the appropriate materials of construction, the appropriate injection point. I will tell you all that for sludge conditioning applications, for example, Chimera custom fabricates a Schedule 80 PVC injection insert in dispersion ring that we put into a sludge feed line at a plant to ensure that there is no corrosion. This has proven quite effective at all of our applications. I can proudly say that our struvite mitigation applications that we have in place that for multiple years, in some cases exceeding 12, 14 years, we've never had an issue with corrosion in the pipe.
Yeah, Richard, Mike's asking about iron binding sulfur over phosphorus.
Well, it generally, depending on the application point, the iron is going to go after the sulfide first before the phosphorus, but it's a rapid situation. So some of you probably use iron right now at plants for phosphorus removal, and that you find during the summer your iron demand increases, and that's due to a higher level of sulfides. The iron is removing both. I hope that I've answered that.
Well, guys, we are at time. I wanted to take a second to thank Brett and Richard for a great presentation today. And another thank you to Chimera for sponsoring today's event. This concludes today's webinar, and we thank you all for attending. The recording will be available at wefbuyersguide.wef.org. We will send our registrants an email tomorrow with that link. Please visit our event calendar to sign up for future events, and we hope you guys have a great day.
Oh, it's too many.
Thanks all for attending.
Thanks, Dylan.
Thanks, Dylan.